Good day, everyone. So, today we will be talking about thermodynamics and fluid phase equilibria for your computer applications in chemical engineering. The objectives of this topic are as follows. We will be able to solve for the vapor pressure of pure substances and to determine the boiling point or the bubble point of a mixture, and as well as its dew point. And we will be able to calculate the relative volatility and as well as solve molar volume using uh, equations of states, and of course place the effect of temperature on density. So phase equilibrium thermodynamics is when two phases are brought into contact. A redistribution of components of each phase occurs through evaporation, condensation, dissolution, and or precipitation until a state of equilibrium is reached in which the temperature and pressures of both phases are the same. The volatility of species is the degree to which the species tends to be transferred from liquid phase to the vapor phase. And sometimes the estimation of vapor pressure can be carried out by an empirical correlation, which we will be talking about later. Let's go first to the boiling point. When we are heating a liquid consisting of two or more components, the bubble point is the point where the first bubble of vapor is formed, and the vapor will probably have a different composition in the liquid. And also the bubble point and the dew point at different compositions provide, of course, useful data when we are designing distillation systems. So this is the equation for calculating the bubble point. The condition must be set that such that the sum of Ki times Xi should be equal to 1. So what is Ki? Ki is known as the distribution coefficient, which is defined as the ratio of the mole fraction of the vapor phase Yi to the ratio of the mole fraction in the liquid phase, which is Xi, at equilibrium. For mixtures that Dalton's law and Raoult's law hold, K is defined as the ratio of the vapor pressure to the total pressure of the system, which is in the case of ideal solutions. Next, the dew point. The dew point is the temperature at which the air needs to be cooled to become saturated with water vapor. The airborne water vapor will condense to form liquid water when further cooled. If air cools by contact with a surface that is cooler than the air to its dew point, the water will then condense on its surface. Let's go ahead to the correlations for vapor pressure. So, Antoine equation is the most successful correlations in estimating the vapor pressure of a particular substance. It uses three coefficients that are unique of the substance. So these coefficients are A, B, and C. I have placed an Excel file here for you to download, and these are the data for your Antoine constants. Take note that there is a minimum and maximum temperature upon which these constants are limited. Okay. For distribution coefficients, we have the Prester charts. So they are usually a convenient source for determining the K as a function of temperature and pressure. Okay, relative volatility is defined as the following equation. Take note that the K factor is heavily dependent on the temperature due to the changes in vapor pressure. But the relative volatility for the two components only change moderately with temperature changes. So that is why it is usually preferred when um, designing distillation systems. Let's go ahead to the steps in calculating the boiling point. So the first one is that we need to assume the temperature, and then we will try to solve for the vapor pressure of each component using the Antoine equation, and then we will solve for the yi, which is the kixi, and if the summation of yi is equal to 1, then we end, because that assumed temperature is our boiling point, I mean bubble point. Okay, so if not, then we will go ahead and assume another temperature. Let's go ahead to some example. So find the bubble point temperature for a mixture of 35% mole N-hexane, 30% N-heptane, 25% N-octane, and 10% N-nonane at 1.5 atm total pressure. So I will pause for a while because we will try to solve this using Excel. Okay, so welcome back. So the first thing that you might want to do is to list all of the components that you are trying to solve. So we have the N-hexane, N-heptane, N-nonane, N-octane, and N-nonane, and their respective liquid phase mole fraction. So when you open that file that I have linked in the PowerPoint slide, you will have a data of different substances and their corresponding Antoine coefficients. Since we are concerned with the following components, we will just try to copy the A, B, and C. So the first one is N-hexane. So N-hexane is here. So we will just make a table. A, B, C, then Xi, then N-hexane. Great. And then the next is N-heptane. Then N-octane. The last one is N-nonane. Okay. So the next step is to calculate the vapor pressure, right, from our flowchart. So we write this as P sub I. And this is the Antoine constant. I mean the Antoine equation. So let us try to type it here. Equals, since it is log, we need to raise it to 10. Then A is this one minus B, B divided by, so we need to assume a temperature. So let us put the temperature somewhere here, plus C. Okay. Since this is in mmHg, take note that the total pressure given in the problem is 1.5, right? We will just try to divide this by 760. So this is the temperature, the assumed bubble point temperature. In degrees Celsius, let us first assume at 110. Let me copy the problem. Okay, so we have a total pressure of 1.5. Yeah. Okay. Next, what we will try to do is that we will try to do the same. We can manually, the same for the n-heptane, you can manually change the equation here and do the same for the n-heptane, but we just like to um, drag it down. Okay, so as you can notice, it will also drag down the temperature, the cell, the reference for the temperature cell. So what we will try to do is to fix that by introducing dollar $B dollar 14. Since our temperature is located at B14, we will introduce dollar dollar. Once you have done that, it will fix the cell at this particular value. Okay, and when you drag it down, it will also drag down for the n-heptane. All the Antoine constants for different substances will also be followed. And there you go. Right. So these are the corresponding pressures of each component at 110 degrees Celsius. Next, we will try to solve for the Ki. Take note for the conditions that we have stated earlier. The Ki for where Dalton's law and Raoult's law are applicable is just the ratio of the vapor pressure to the total pressure. So what we will do is to divide this by the total pressure, and then that is our Ki. Oops. Let's try to fix the pressure as well. And there you go. Next, we will try to solve for the Yi. Take note that the Yi is just equal to Ki times Xi. So let us drag this down. And the condition is the sum of, let's just say sum of Yi, Y sub I is equal to, so this is just basically adding all of the Yi's. So obviously the Yi is not equal to 1, therefore we need to change the temperature such that the sum of the Yi should be approximately equal to 1. So you can actually do this manually. You can type 102 or 103, but in order to solve that quickly, we will try to use the solver function of the Excel and as well as the goal seek. You can actually try to solve the problem either using goal seek or solver. So the first thing that you will do is go to file, then options, then go to add-ins. Scroll down until you see Excel add-ins. So once you see this one, make sure that you check the solver add-in and then click OK. So the first method that I will teach you is the goal seek. So I want you first to go to the data tab and then click on what if analysis and then click on goal seek. So we need to set the cell which is the yi, the sum of a yi, to a value of 1, right? Because that's how we determine the vapor pressure. I mean the bubble point. Kixi is yi. So 1, by changing the cell, so since we are trying to change the temperature and solving for the bubble point, we change this cell. Then once you click OK, it will try to solve, and the current value is now 1.0008, which is fairly good. And we can say that the bubble point is at 105.4 degrees Celsius. So that is the goal-seek function. For the solver, let me try to clear this one. For the solver, we can also do that. So set the objective. So this is our objective to a value of 1 by changing the cell for the temperature. Then click solve. So it says that it has found a solution. All constraints and optimality conditions are satisfied. So click on keep solver solution, then click OK. So it also solves for um, the bubble point, which is at 105 degrees Celsius. Okay, so what you will be using in this class, the type of simulator that you will be using is DWSim. So this is an example of a process simulator. Later on, I will discuss to you in detail the use of this process simulator. First, let us just for the sake of familiarization and using the simulator, we will try to solve the previous problem using DWSim. So let's go and click on create new. Okay, this is the simulation configuration wizard. This is where we will input our compounds or components and select an appropriate property package. Let's click on next. So we have the N-hexane. Once you have that, make sure that you click on check heptane, octane, and then we have no name. Okay, once you have selected all the property or all of the components, let's just click on next, and let us just choose Peng Robinson for now. I will teach you how to select an appropriate property package later on this course. So click on next, and if you want to customize the following units, you can select any of these predefined units, or you can just click on clone and try to customize each unit to what you want. So I like the pressure to be in atmospheres and the temperature in degrees Celsius. So once you are there, let's go and click on the material stream, click and drag, then you will have this one, MSTR. So once you click on that stream, the default property package will be set, which is the Peng Robinson. So let us first try to input our info in the input data tab. Make sure you click on compound amounts, and the basis should be on mole fraction. So because this is what it is given in our problem, you can actually input mass fractions, mole flows, mass flows, etc. So let us set the hexane, heptane, and octane, and then the name. So make sure that the total for the mole fraction and mass fraction should be equal to 1. And make sure once you have made some changes here, click on accept changes. Otherwise, it will stay on that same mole fraction earlier, which is 0.25, 0.25, 0.25. Okay, make sure you click on accept changes. Go back to stream conditions. The flash spec, since we all already know the total pressure, should be pressure. And then, in the case of estimating the bubble point, we should set the vapor fraction equal to 0. So, as you can see, it has already calculated the temperature, but the pressure is at 1 atmosphere. So, what this basically means is that this is our bubble point of this mixture at 1 atmosphere. So to change that, make sure you select that and type 1.5 for the total pressure, and make sure that you press enter to make appropriate changes. There you go. So it says that the temperature is 106.562. As you can see, it's somewhat um, different from what we have calculated. The difference between these two results is just basically due to the interaction of each components, because again, we have just assumed that for this problem, Raoult's law and Henry's law applies. But in reality, there are interactions between these components that will generate or deviate from the ideal or from the solutions that Raoult's law and Henry's law apply. So, which is the more accurate solution? Of course, this one, because it already accounts for the interaction between each of these substances present in our solution. This is just a simplified calculation. So you can actually verify this answer on another simulator. We'll try this on HYSYS. I will show you the different answers on HYSYS based on the type of property package that you are using. So N-octane and okay, fluid packages. So since we don't have an Antoine property package in our DWSIM, but HYSYS actually has Antoine property package, so we will use this. So as you can see, it gives you a different parameters in Antoine. It actually has 1, 2, 3, 4, 5, 6 coefficients for that. So we can expect that the result of this Antoine property package is somewhat nearer to our Excel solution. I'll just add some material stream. Okay, setting the vapor phase fraction, say equal to 0, the same as in DWSIM, and the pressure is 1.5 atmospheres, and assuming a mass flow. So take note that you should input a mass flow here, otherwise it won't solve for the bubble point. So let us input 1. So unknown compositions. So that is 0.35, 0.35, 0.3, 0.25, 0.1. So click OK. Then, so the temperature is 221.9, and in degrees Celsius, as you can see, it is 105.5. It is somewhat near our solution, which is 105.34. This is because we use the same property package, which is the Antoine. But if we try to change that property package, which is a more realistic one, so I won't stay in the hold mode because I want it to calculate in terms of the Peng-Robinson property package. As you can see, it changes the bubble point at 106.2, the same as the result in the WSIM, which is 106.562. So take note that we will not be using HYSYS for our class, and we will be using primarily the WSIM for all of our simulations. So it is important for you to interpret the differences in the results between our example here in Excel and our sample here in simulator.